So as we said on the last slide, you don't always need to look at a graph in order to determine the limit. Sure, if we had a graph, we could look as x approaches a number on the graph, and we could determine if the graph itself, if the function is approaching a certain y value. And again, as we discussed, it has to approach the same y value on both sides of the x value. But we also said that sometimes graphing is not really fun. And so there has to be another way. And so substitution is the first way that you would try to see if you can get the answer to the limit. So let's look at this first one. This first one says, find the limit as x approaches 0 of this function u of x. Well, if we substitute in x as 0, yes, we get the number 1. But my concern is, even though I know that u of 0 equals 1, my concern is that at x is 0, there's the breaking point of this piecewise function. So let me go ahead and graph it because I'm not positive of this situation, right? So whenever you're not sure, you graph it. So where x is less than 0, my y value is 0. That means that to the left of 0, y equals 0 is being graphed. To the right of 0, y equals 1 is being graphed. So here's what's happening here. At x is 0, even though we can substitute 0 into this piecewise function and get an answer, if we are looking at the limit as x approaches 0, if I'm on this piece of the function, my y value is approaching 0. Whereas if I'm on this piece of the function, my y value would be approaching 1. So this is starting the concept of one-sided limits. One-sided limits say on the left of this function, u of x, my y value is approaching 0. But on the right side of 0, the function is now approaching 1. So because the left side of 0 and the right side of 0, because those are not equal, it means that the limit as x approaches 0 does not exist. And we abbreviate does not exist with DNE. Again, it's because both sides are pointing to two different places. Let's look at this other piecewise function. So if we went to go graph this, when x is 0, the piecewise function says y is 0. When x is 0, y is 0, this just makes a point. The rest of it says 1 over x squared. So when x is 1, y is 1. When x is negative 1, y is 1. When x is 2, y is 1/4. When x is negative 2, y is 1/4. So what's happening here is that we have a vertical asymptote for the first piece. We also have a horizontal asymptote at y is 0. So now what's happening? Well, now they're asking for the limit as x approaches 0 of this function g of x. And as we're approaching 0, again, what's happening here is that this side of 0 is going up to infinity. This side of 0 is also going up to infinity. And so again, this really does not exist. Some people may say that it goes to positive infinity, which you could see the argument for, because on both sides of x is 0, your graph is pointing upwards. So in a way, they are going towards positive infinity. But for now, we could either say goes to infinity or does not exist, because we're not pointing to exactly the same definitive point. Technically, you're not supposed to be able to get to infinity. Now the next one. So in the next one, yes, I could go about graphing this. It's going to make a strange graph, I know for sure, because not only is there a square root involved, but there's also an x squared underneath it. So instead, I'm going to use that other concept, which is sometimes it will work if we actually substitute the number, the value of the limit in for x. Sometimes it works. So one technique is to try substitution. So I'm going to go ahead and I'm going to substitute -2 in and see if I can actually physically get a real answer. So -2 squared is 4. 4 times 4 is 16. 16 plus 3 is 19. So yes, a limit exists, and the limit would be equal to square root of 19. Let's try this one. Let's see if substitution works. So you get -1 cubed, 4 times -1 squared, minus 3, over -1 squared plus 5. Does substitution work? Well, if we can get an answer, then it works. So -1 cubed, 4 times -1 squared, -1 squared, 3 minus 3 is 0. Can you get an answer if 0 is divided by 6? Why, sure. Your answer is 0. The next one. Let's substitute in 1. We're on a roll. 1 squared plus 1. Oops. No square. 1 squared plus 1 minus 2 over 1 squared minus 1. On the top I got 2 minus 2, which is 0. On the bottom I have 1 minus 1, which is 0. Ow. There's an ow situation. So substitution's not working here. We're dividing by 0. That's not possible. So if substitution doesn't work, the next thing that I might try, especially on a rational function, is can I simplify this rational function? So let's go ahead and factor the top of the function. Let's go ahead and factor the bottom of the function. And hey, look at that. There's actually a hole at x equals 1. So now let's take what's remaining, because all that we know so far is that there's a hole at x is 1. Let's take what's remaining and do a substitution now. So does substitution work now? If I substitute in 1, I get 3. So because of that, I know that the original answer is 3, even though I know that there would be a hole there at 1, 3. Both sides would be approaching 3. Again, on the next one, you notice that if you substitute in 0, you end up dividing by 0. That's kind of a problem. So let's see if we can simplify this function. So let's go ahead. I'm going to use the conjugate, because the conjugate's very magical. And I know from experience that sometimes if you multiply the top and the bottom of a fraction by a conjugate that you see, sometimes it helps things to fix itself. I think it's the secret of life, the conjugate. When in doubt, do the opposite. Okay, so first times first. The outer and the inner cancel, which is the beauty of the conjugate. Last times last, negative 100. Oops. So now on the bottom I have x squared times the square root of x squared plus 100 plus 10. On the top, I get x squared. Thus, the x squares can cancel. And so we've reduced the fraction. So now let's try 0 and see if it works. It's looking pretty good. I have square root of 100, which is 10, plus a 10. So the answer would be 1/20.